Good evening, sir.
Good evening, Miraj.
Good evening, guys.
Good evening, sir.
Yeah. So we'll start the class. Okay. So yesterday we discussed about the UART communication, right? So what is mean by UART and the HAL programming, bare metal programming of HAL programming of this UART and all these things we saw yesterday. Okay. So today we are going to see the next serial communication. So this one we already did. This USART. Okay, that is UART we already did. And today we are going to see this SPI protocol. Okay, so we'll see what is SPI, how to configure the SPI, how to transfer the data, all these things we will see today. So today's topic is SPI communication. Okay, again, SPI communication, you people have already studied this in your PIC microcontroller. Okay, so same thing we are going to see here also with HAL APIs. Okay, a much simpler HAL APIs. Okay, so first thing, SPI. What is SPI?
Serial peripheral interface.
Okay, so what is serial peripheral interface? Okay, it's serial peripheral interface. Okay, fine. What is serial peripheral interface? What is mean by that? Okay, what
Like
type of
the
communication this is?
external,
Hmm.
this is the synchronous serial type only.
Okay, it's a serial communication only. It's a synchronous type. Okay.
Yeah, we can connect with the like, devices with the external devices
Hmm.
over this communication, like a master and slave.
Okay. So Arvind and Venkatesh. Just a minute. Yeah. Okay. So SPI is an serial peripheral interface. It is an master slave communication. Okay. So by using this UART or USART, it is a very simple communication. Already told you this UART or USART is a peer-to-peer communication. That is, it is a one-to-one communication. Okay, we can able to transfer from one device to another device, or we can able to connect one device to another, only one device at a time. Okay, so we can able to transfer the data uh, in this UART from a peer-to-peer communication. Okay, but this SPI is we call this as it is a serial communication only. Okay, and it is a synchronous communication. Okay, so we saw what is synchronous communication, right? Synchronous communication means it requires a clock pulse to transfer a data. Okay, and also this SPI is an master slave communication.
Which mean only one direction. Up duplex will be there.
Which one?
This one.
No, it is a full
It is a
duplex.
up duplex.
No, SPI is a full duplex. Only I2C is half duplex.
Okay.
Yeah. So I'll tell you how to find this half duplex and full duplex. Okay. This SPI is an master slave communication. That means we can able to connect multiple devices at a time. Okay. This SPI is otherwise, or we can able to call this as an multi-master, sorry, single master multi-slave communication. So we'll be having a one master device and multiple slave devices. We can able to configure multiple slave devices, and we can able to transfer the data from master to slave or from slave to master. Okay, so that depends on how you are going to connect with the devices. Okay, so how we are going to connect, or what are the pins available in this SPI is, okay, let's assume this is one device and this is an device number 2. Okay, so in what we have only 2 pins. Okay, one is an TX and RX. Apart from that, we'll be connecting ground. Okay, but we'll be having only 2 pin communication. Okay, so here let's assume this is your master device and this is your slave device. Okay, so this SPI is having a 4 pins. So here we'll be connecting from master to slave by using 4 different OS. Okay, first one, since it is a synchronous communication, we require a clock pulse, right? So this is a serial clock. Okay, so here also we'll be having a serial clock. Okay, and next one we'll be having something called as an MOSI, MOSI. I'll tell you what this MOSI is. Okay, and next one is MISO, MISO. This is MISO. Okay, and the last one is we have SS bar. Okay, SS is nothing but it is a slave select, or we call it as a chip select or a slave select. Okay, so there are 4 pins available in the SPI communication: serial clock, MOSI, MISO, and SS. Okay, now we will see one by one what these things are. First one, this SLCK is nothing but it is a serial clock. Okay, so we'll be having a clock pulse, and this clock pulse will be transferred, or this clock pulse has to be synchronized between master and slave so that it can able to transfer the data through this clock pulse. Okay, that is the first thing. Second thing, MOSI is nothing but it is an master out, slave in. Okay, that means the data will be transferred from master to slave. So master will be the output and slave will receive the input. Okay, so that is master out, slave in. Okay, and the next one is MISO, is master in and slave out. So now master is going to get the data from the slave. Okay, and slave is going to transfer the data to the master. Okay, so this is master in and slave out. Okay, and the last one is an SS. SS is nothing but it is a slave select. So here we will be having a multiple slaves, right? That's what we saw, that single master, multiple slaves. Okay, so we need to select which slave I need to transfer the data. Okay, so that is the last pin. That is SS bar, SSN slave select.
How many slaves are we can connect?
You can able to connect up to 128 slaves, I think.
1 byte.
No, 128 is
0 to
2 power 8.
127.
Yeah, 0 to 127.
Then 1 byte. Sorry, 7 bit.
Yeah, 7. Mm, 2 power. Yeah, 2 power 7 is 128, 127, right? No, 2 power 8 is 127. 2 power 8 is 256. So that means 128. Yeah. Mm, wait. See, it's an address based. Okay. only this I2C you'll be having a 7 bits of address so that you can able to connect up to 127 devices. In SPI, you can actually able to connect as many slaves you want. Okay, there is no limit. The only limit is the slave select pin which is available for you. Okay, the slave select pin is nothing but it is your GPIO pin. Okay, if you have more GPIO pins, you can able to connect that much amount of slaves. Okay, so there is no um, limit for that in SPA.
Okay, sir.
Okay. So this SS in some devices we call it as an CS. Okay, that is in chip select or slave select. Both are same. Okay, so we'll be having an CS or an SS. So these are the 4 pins available in the SPI communication. We call this as an 4-wire communication also. Okay, so I'll be having 4 wires for transferring the data. Now, this transfer of data can be done by using 3 different methods. One is we can able to use modes. We can able to use this in a simplex, and we can able to use it as an half duplex. We can able to use it as a full duplex. Okay, so simplex is an one way of communication. Okay, either you can able to transmit a data or you can able to receive a data. Okay, that is an simplex. It's an one way communication. You can't able to perform both operations in a single device. Okay, either this device will transfer and this device will only receive the data. Okay, or this device will transfer the data and this device will receive the data. Only one operation can be performed. Both operations cannot be performed in a single device. Okay, that is one way of communication, that is simplex. Off duplex is a 2-way of communication. Okay, but the data transmission will not happen simultaneously. Okay, that means either you can send a data or you can receive a data at the given period of time. Okay, you can't able to do the same transferring and receiving at a time. That is not possible in the off duplex mode. Okay, first you have to transfer the data, then on the next cycle you can able to receive the data. Okay, so that is a possible in off duplex, whereas full duplex it is a 2-way communication again, but also you can able to receive and transfer data at a time. Okay, that is in full duplex. Okay, so this TX and RX can be done simultaneously. Okay, so these are the modes we can able to use this SPI, whether you are going to use this SPI for only transmission or whether you are going to use this SPI only for a receiving. Okay, so that is we can able to decide these modes in the SPI. Okay, now this is an single master and single slave communication. Okay, now if I have a multiple slaves, okay, how to connect a single master with the multiple slaves? Okay, that we are going to see now. For example, let's say I'm having one. Okay. So let's assume I'm having two different registers. One is for transmission, one is for a receiving. And the next two are, I'm just going to copy this, paste here, and this. Okay. Yeah. So let's assume this is my TX register and this is my RX register. Assume this is my master device. This is my slave number 1. Okay. And after that, we'll be having one more device over here, which is called as slave clock or SPI clock. Okay. So this clock will be transferred to this TX register, RS registers, and all these things. Now, let's assume this is my slave 1, right? Similarly, I'll be having a multiple slaves over here. So assume this is my slave number 1 and this is my slave number 2 with a different color. Okay, and I'm having a slave number 3 over here with a different. Yeah. So again, the same thing. This is TX. Okay, this is my RX register. And this is my TX register. Okay, and similarly, this is my RX register here. And this is my TX register. This is my RX. This is my TX. Okay. So apart from this RX and TX, we'll be having one more thing that is, I'll put it in the red. Okay, we have one more thing that is the slave select. Okay, let's assume this is my slave select. Either SS bar or CS bar. Okay. So depends on the data sheet. It can be either an SS or a CS. That. Okay, so why I'm explaining all these things in detail is, as I already said to you, communication protocols are most repeatedly asking interview questions. Okay, you need to be thorough in depth of all this communication protocol, how this communication happening with each and every protocols. Okay, for UART, USART, CAN, I2C, SPA, all these things, you need to know how these data are transmitted. Okay, so you need to be thorough with that. Okay, now this TX register from the master is going to transfer to this RX. Okay, that is the first stage. Okay, so TX register is going to transfer the data from the to the RX of the slave. And similarly, this is going to transfer the data to this one. Okay, this is in the green color. Right, so we call this one as the MOSI, since the master is out and slave is in. Okay, and this one is, we call it as a MISO, that is master is in and slave is sending the data, output data. Okay, now this same MISO, MOSI and clock is giving to all the slaves. Okay. Now I'll just give the clock pulse. Okay, I'll just put this here. Okay. So this clock is being transferred to both this TX RX register. Also, not only that, for all this TX RX in the slave devices is being transferred for the same clock. Okay, let's assume. Okay, I'm just giving this clock over here. So this clock pulse is common for both the slave devices as well as this master device. Okay, so the clock pulse is being shared to all these devices. Since it is a synchronous communication, the clock has to be matched with all the devices. Okay, now I have connected one slave with this MOSI and MISO. Now I need to connect this slave number 2, slave number 3. Okay, so let's assume this is my slave number 2 and this is my slave number 3. Okay, so the data will be transferred is we don't have any other external MOSI or MISO. The same MOSI MISO has been transferred to the devices over here. Okay, let's assume this is MOSI, right? Okay. Blue color. Okay, here the same data has been transferred to this MOSI slave 1, slave 2, and again this slave 1 and slave 2. The same data has been transferred. Okay, that is same wire has been connected to all these RX register, and similarly for this TX registers also we'll be having the same wire connection. So this will be having one TX and here we'll be having another TX. Okay, so all the TX are connected. Did I give it in the wrong way? Yes, I did. Okay. Yeah. So this is my MISO, right? So the TX has to transfer the data over here. Mistakenly given this. This is again in this direction. Okay. So this TX and RX pin of this master is being shared to all the slaves. Okay, even if you have some 30 different slaves, all the 30 slaves will have the same MOSI and MISO wire. Okay, we'll be just connecting this wire to all this RX and TX register of the slaves from the master. Now, imagine if a master is transferring a data to this MOSI, all these slaves will receive the data, right? Since it is being connected. Okay, so everything will receive the data from this to this to this. All these things will receive a data. Okay, so in order to avoid that, or in order to communicate with a particular slave, we'll be having something called as a slave select or a chip select pin. Okay, so now this slave select or a chip select pin is nothing but it is a simple GPIO pin. Okay, let's assume I'm having a PA0, PA1 and PA2. These 3 pins I'm using here. Okay, GPIO PA0, PA1 and PA2 pin. Okay, now I'm connecting this PA0 pin to, let's assume I'm just connecting to, okay, wait, yeah, this one. Let's assume I'm just connecting this PA0 to this slave select. Okay, and PA1 to this slave select and PA2 to this slave select. Okay, so I'm just connecting this slave select pin to this GPIO pins. Okay, if I make this particular GPIO pin as 0, that means if I make this PA0 equal to 0, that means slave 1 will be selected. Okay, I'll just make these two are 1 1. PS0 equal to, okay, I'll just put it here. PS0 equal to 0 1 1. If I set this value, then slave 1 will be selected. Okay, for slave 2, it has to be PA0 equal to 0, PA1 equal to 1, sorry, PA0 equal to 1, PA1 equal to 0, and PA2 equal to 1. Okay, that means slave 2 will be selected because PA1 is being connected to this slave select. Okay, so in order to select a particular slave, I need to make that slave select pin as a logical 0. Okay, so that whatever data I am transferring from this MOSI or requesting in this MISO, okay, that particular save will be selected by using this logical 0 pin. Okay, so if it is slave 3, again the same thing. PA0 will be 1, PA1 will be 1, and PA2 becomes 0. Similarly, you can be able to connect multiple GPIOs. How many GPIOs are available in your particular microcontroller? You can be able to configure all these GPIO pins to that much amount of slaves. So that's why I already told you this SPI doesn't have a limit for a slave device. Okay, if you have 40 different GPIOs can be assigned for a slave select, that is fine. You can be able to assign for 40 different slave select and you can be able to use 40 different slave. Or if it is only 10 pins are available in the GPIO for slave select, just connect 10 different slaves and you can be able to use it. Okay, so only the amount of pins available in your device is what the limitation of the how many slaves you can able to connect. Okay, so this is how the single master multi-slave communications will be happening in the SPI. Clear? Any doubts in this?
Sir, we have a GPIO of 3 pins. Can't we connect with 2 power 3 8 also? 8 device?
Yeah.
Or like
That's
a
what I
number of
said.
GPIOs?
Number of GPIO. Oh, these 3 pins you are saying you need to connect with the ETA.
Possible.
No,
It's
no, no,
2
no.
power 3.
No, it's not actually 2 power 3. See, it's not working like 0, 0, 0 means
0
one
0.
slave will be selecting, 0, 0, 1 means another slave will be selecting. It's not like that. You have to make this logical 0 for that particular pin to activate. Okay, so you will be having only 3 options. Either it is 0, 1, 1 or 1, 0, 1 or 1, 1, 0.
Okay.
Okay. So this is first device, this is second device, this is third device.
Okay, sir.
Yeah. Single master, multiple slave. Okay, is it clear? Any doubt? If you have any doubt, just ask me, I will explain it, or else we will go to the next format, communication format.
Okay, sir. Understand.
Mm-hmm.
Okay, sir. Understand.
Yeah. Okay.
இப்போ I2C SPI வந்து எந்த நேரத்துல சார் யூஸ் பண்ற மாதிரி இருக்கும்? இப்போ ரெண்டுத்துக்கும் டிஃபரன்ஸ் இருக்கு, பட் ஆனா எந்த மாதிரி சுச்சுவேஷனுக்கு இது யூஸ் பண்ணுவோம்?
Okay. So I2C will be useful for the high data speed.
Okay.
I'll just write it over here. Okay, I2C can be useful, for example, in your board. Let's assume your microcontroller. This is your microcontroller. Okay. if it has to transfer data to something like an EEPROM. Okay, so EEPROM has some data. It has to take the data and process or transfer the data to this EEPROM. Then this communication will be happen in the I2C, sorry, SPA. Okay, and similarly, if you have something called as a flash memory.
Okay.
Okay, this flash memory communication from microcontroller will be happen in the SPA method.
Okay.
Okay, and if you have any display devices like let's say you have something like an LED display, OLED display. Okay,
Yes,
yeah, that OLED display will be communicated with an SPA only. Okay, if it is very short distance.
Serial clock and serial data pin தானே சார் இருக்கு
எதுல
OLED டிஸ்பிளேல OLED டிஸ்பிளே
OLED display. OLED டிஸ்பிளேல இல்ல மிசோ மோசி இருக்குமே, ஒரு நிமிஷம் செக் பண்றேன்.
லார்ஜ் சைஸ்ல வந்து SPI இது இருக்கும், ஸ்மால் சைஸ்ல வந்து I2C இருக்கு.
Okay, we have an I2C here. Okay, we have an I2C here in the OLED display. Okay, some OLED devices having an SPI communication. Okay. So any onboard communications happening inside the board, that is an SPI communication. Mostly 90% onboard communications will be configured in a SPI only. Okay.
Okay.
Yeah.
Onboard in the sense the board, one board to another board.
No, your microcontroller with some other peripherals attached to the board in a single board. See,
Okay,
you have
I remember one sensor, sir. That sensor is ultrasonic sensor, I guess.
Okay.
So that is a SPI or a UART, sir?
Ultrasonic sensor is a digital sensor. So there is no need for any communication protocol over there. It is just going to transfer a digital pins. ILO pin, that's it.
Okay. We will get some values, I guess. Like
no, ultrasonic sensor, it is just going to transfer some pulses like this. Okay. We will just count the number of pulses for a particular time period, and then we'll just calculate the distance.
Okay.
It won't transfer any values kind of thing. Only the pulses will be there.
Got it.
Okay, so this onboard communications or SPIs, and if you want to transfer the data from one board to another board, then you will be going for the I2C. Okay, because the number of wire connections over here, you can see if I want to connect on 3 slaves, you can see the number of wires I required for this. Okay, but for the internal communication, this is very simple. Like I can just solder this pin, or I can able to print this connection internally inside the board, and I can able to transfer the data. But if it is a wire connections from the outside of the board, then that is very difficult, right? For this much of communication. So we'll be mostly using that for I2C. Okay, because I2C is a 2-wire communication, we'll be having only serial clock and serial data. Okay, so that we'll be using I2C for any external communication data transfer, and internal board communication we'll be using SPI. Clear?
Okay, sir.
Yeah. Okay, so the next one is as like your UART will be having a communication format over here. Okay, so there are some parameters we need to set for when this data has to be transferred and when this data has to be read. All these things we need to configure. Okay, so the next thing is SPI communication format. Okay, so this SPI communication format, before going to this SPI communication format, we need to know some terms. Okay, some terminologies we are going to use in this communication format. Three terminologies. One is serial clock phase. Okay, that is CPH, clock phase. Okay, CPH. And the next one is serial clock polarity. That is CPOL, POL. Okay, and the next one is we need to know about data frame format. That is the DFF. Okay, we need to know what these things are. Okay, this serial clock phase and serial clock polarity, you can actually able to assign two different values to this. Either you can able to assign a 0 or you can able to assign a 1. And similarly, you can able to assign a 0 for polarity and you can able to assign 1 for this polarity. Okay, based on this, you can actually able to use this SPI in 4 different modes. Okay, that is phase 0, polarity 0, phase 0, polarity 1, phase 1, polarity 0, and phase 1, polarity 1. Okay, 4 different modes you can able to use, and you will see what this phase, what this polarity, and all these things. Okay, so before knowing this serial clock and serial phase, we need to see two different things. One is the data toggling. And the next one is data sampling. Okay, so data toggling is nothing but here again, since it is in serial communication, the data will be transferred bit by bit, right? That is what in serial communication is. We saw on the first class, that is day before yesterday. Okay, so data toggling is the data transition from one bit to another bit. That is what called as a data toggling. Okay, so the data transition from one to another bit. Someone's mic is on, not mute. Augustine, yeah, okay. Okay, so data transition from one bit to another bit, we call it as a data toggling. For example, if you want to transfer a data like 10110110 1 2 3 4 5 6 7. Okay, if you want to transfer a data something like this, okay, first the data will be 1. Okay, then the next toggling data will be 0, and the next toggling data will be 1. Okay, and the next toggling data will be 1. Okay, something like that, it will go on. So this will be your 1, this will be your 0, this will be your 1, this will be your 1. This particular line, we call it as a data toggling. Okay, so data has been transferred from one bit to another bit. Again, this bit to the next bit. Again, this bit to the next bit. Okay, we call this as a data toggling. Okay, remember this. This data toggling and data sampling will be varying based on these 4 modes. Okay, we need to know what this thing is. And the next one is data sampling. Data sampling means when you are going to capture or collect the data. That is what called as a data sampling. Capture or collect, or I'll just put capture or read the data. Okay, so that is what called as a data sampling. Okay, this is like, for example, if you're having a pulse like this, okay, because since it is a synchronous communication, all this data transmission will be happening with the pulses only, right? Okay, so when you are going to capture the data or read the data is what called as a data sampling. Whether you are going to read the data on the I pulse, that is whenever it is a transition from low to I, you are going to read the data, or whether from I to low, you are going to read the data. Okay, So that is what the data sampling is when you are going to read the data. Okay, so whenever the clock pulse happens during this low to high clock pulse, you are going to read the data, or whether from the high to low clock pulse is happening, you are going to read the data. That is what called as a data sampling. Okay, so this data toggling and data sampling will be varying based on this serial clock and serial clock phase and polarity is going to define when you are going to toggle this data, when you are going to sample this data. Okay, so that we are going to see right now with an timing diagram. Okay. Is it clear so far? What this
So
data
one more
toggling?
time, can you explain a data sample?
Data sampling. Okay. Data sampling means okay, your data will be transferred with the clock pulse. That is what a synchronous communication, right?
Yes, sir.
Okay. So if the data is transferred from the TX to RX, okay, this RX has to read the data. Okay. Now, when this RX has to read the data is what called as a data sampling. Whether during the I pulse, that is a transition from low to high, I'm going to read the data, or from high to low, I'm going to read the data.
Okay, we need to inform to the
Yeah.
slave that.
Yes.
Okay. Like
You need to inform
yesterday,
the
we
slave,
also
right?
like.
Okay, whenever there is a transition from high to low pulse, read the particular data. Okay, so that is what
Okay.
called as is this data sampling.
Okay, sir. Got it.
Okay.
Got it.
Okay, now we'll see what this clock phase and clock polarity individually. Then we will see how it will be combined. Okay, so first we will see the clock polarity. That is simple one. So CPOL. As I already said, CPOL is going to be having a two different values. One is 0 and the next one is 1, right? Okay. If this clock polarity is 0, that means your serial clock low level is idle. Okay. That means in your clock pulse, for example, if it is your clock pulse, okay, all your low pulses are ideal condition. Okay, nothing will happen during that, or we call it as a 0. Okay, this is idle and all these things. Okay, or in our language, this is 0, this is 1 if the clock polarity is 0. Okay, but if the clock polarity is 1, which is quite opposite to that of this, that means your serial clock high level is idle. Okay, that means in the clock pulse, okay, this will be idle. Okay, that means this pulse is 0, this is 1, this is 1, this is 0, something like that. Okay, it's not exactly 1 and 0. For your understanding, I'm saying, okay, this will be your ideal condition and this will be something will happen in this low pulse. Okay, so that is what a clock polarity 0 and 1. Clock polarity 0 means all your low pulses are ideal condition. Clock polarity 1 means all your high pulses are ideal condition. Okay, this is clock polarity 0 and 1. Okay, and similarly, there is something called as a clock phase. Okay, again, this is having a same 0 and 1. Okay, here if a clock phase is 0, that means your low pulses are trailing pulses or trailing edges. Okay. And your I pulses are leading edges. Okay. And this is exactly opposite to that of your low pulses are leading edges. And your I pulses are trailing edge. Okay. So what is mean by this trailing edge or what is mean by the leading edge? Yeah. Yes. You're saying something.
No, sir, I about to ask what is this trailing and
Okay. So this trailing edge and leading edge is what going to define in this clock polarity. Okay. So here in the clock polarity, your trailing edges are 0 and leading edges are 1. Okay. That means I'll draw it over here. This is your trailing edge and this is your leading edge in your pulse. I'll just draw 3 pulses alone. Okay. This is your trailing edges and this is your leading edge. Okay. So in this condition, the trailing means 0 and leading means 1. Okay. And in this condition, the trailing is 1 and leading is 0. Okay. Now you can see if the clock phase is 0 and clock polarity is 0, that means what will happen? The same trailing leading edges will be like this. Or if the clock phase is 0 and this polarity is 1 means what will happen? Okay, all these things we will see now. Okay, so this is what in trailing edge and leading edge is in the clock phase 0. And in clock phase 1, this is exactly an opposite. That is, this is your leading edge and this is your trailing edge. Okay. Yeah. Okay. Is it clear? Okay. Based on this trailing edge and leading edge and this clock polarity, we'll be having 4 different types. Okay. So if you have any doubts so far, just let me know. I will explain it again. Anything, any doubts? Any doubts?
no for me.
Okay. Others? If you have any doubt, just let me know, because if you're not understanding this terms, okay, then here I'm going to draw a timing diagram. Okay, that will not be clear. So if you have any doubt, just ask me right now. Or if you want me to explain it
trailing
again, just
edge-க்கும் leading edge-க்கும் என்ன சார்?
புரியல.
Trailing edge and leading edge difference.
Difference between trailing and leading. Okay. Here
ஆமா.
we saw this polarity, right? Okay. In this one, leading edge means on.
Okay, leading on.
Okay. And trailing means off. Okay. So now you can see over here, this is your off condition. This is your on condition. If the clock phase is 0. Okay,
Okay.
because trailing means off and leading means on, right? Okay, if the clock phase is 1, this is your on condition and this is your off condition.
Okay, sir.
So that is what this leading and trailing, that is going to be work with this polarity. Okay.
பல்ஸ் வந்து லோ ஸ்டேட்டுக்கும் ஹை ஸ்டேட், அதாவது இத லீடிங்க பொறுத்து தான் அந்த பல்ஸ்
ஆமா,
டிபெண்ட்
லீடிங்கை
பண்ணி
பொறுத்து தான்
இல்ல
நீங்க
சார்?
அதை ஆன் ஸ்டேட்டா யூஸ் பண்றீங்களா ஆஃப் ஸ்டேட்டா யூஸ் பண்றீங்களா அப்படின்றது வரும். Okay, it's not always
ஓகே.
the high pulses are on, low pulses are off. You can actually change this high pulses as off and low pulses as on, depends on this clock phase. Okay. Right. So based on this, we'll be having a 4 different types. Type 1, both are 0. Type 2, 0 and 1. Type 3, 1, 0. And type 4, 1, 1. Okay. So we'll see one by one. First is type 0, that is clock polarity is 0 and the clock phase is also 0. Okay, so here I will draw a timing diagram with a serial clock and MOSI. Augustine, can you mute? Yeah, thanks. Okay, so I'm just going to draw a timing diagram based on this serial clock and MOSI. Okay, that is master out slave in. Now, what this type 1, type 2, type 3, type 4 is going to tell you is when this data toggling will happen and when this data sampling will happen. That means when this data will be shifting from one bit to another bit and when can I able to read the value. Okay, so that is what going to define this type 1, type 2, type 3 and type 4. These 2 parameters we need to know. Okay. Okay. Before going to this, these are your pulses, right? As I draw. Okay. These are ideal condition pulses. Okay. In real time, it is not always your pulses will be accurately 1 and 0 like this. Okay. It will not happen in the real time. In real time, what will happen? I will just draw here. Okay. It will not happen. For example, let's say this is my 0 second and this is my second and this is my 1 second on 3 and this is my 4. Okay, let's assume this is 1. It's not exactly in the second it will become to 5 voltage and third second it will become 0 voltage. Okay, third second in the sense it is 2.00000 seconds. This is 3.0000 seconds. Okay, it will not happen like this. In real time, what will happen? It will take a slight deviation to achieve this 5 voltage. Okay, after this 5 voltage, if it want to go to 0, again it will be in the slight deviation like this. This is how your real time pulse will look like. Okay, this is 0 voltage, this is 5 voltage, and again this is 5 voltage to 0 voltage. So when it reaches from 5 voltage to 0 voltage, this might be a very little, something like some millisecond transition will happen. Okay, but there will be a slight curve kind of thing or a slanting ramp kind of thing will happen in this transition of pulses. Okay, this is what your exact pulse will look like. Not like this. This is your ideal condition. That is only theoretical purpose we'll be using this. In practical condition, your pulses will look like this one. Okay. So I'm just going to use the same pulses here in this serial clock. Okay, so serial clock is nothing but it is a clock pulse only, right? So I'm just going to draw the clock pulse. For this one, let's assume this is my clock pulse on, and this is my off. And similarly, this is my on, and this is my off. And this is my on pulse and off pulse. Again, this is my on pulse. Okay, this is how your pulse looks like. Okay, now when your clock polarity and both this clock polarity and clock phase is 0, that means this data toggling, right? Data toggling will happen from high to low pulse. That is, whenever there is an high to low pulse occur, your data will be shift from one bit to another bit. Okay, and this data sampling will occur from low to high pulse. Okay, that means we'll be reading the value in the low to high pulse. Okay, I'll tell you what this one is. So this is your low to high pulse, right? This one. This is your low to high pulse. Okay, so here what will happen? Your data will be data will be sampled. I'll just draw in a different color. Here your data will be sampled. That means your data will be read in your slave device. Okay, and whenever there is an high to low pulse, this is your high to low pulse, correct? Here only from high to low transition is occurring. Okay, and similarly here this high to low transition is occurring, and here this high to low transition is occurring. Okay, so whenever there is an high to low transition occurs, your data is toggled. Okay, again this another data, and here the data will be toggled again. Again this one is another data, and that will be toggled, and it will keep on moving. Okay, like how many bits you are going to transfer, all these bits will be toggled and sampled like this. Okay, let's assume something like an 1011 has to be transferred. This is your 1. Okay, here this toggling happened, right? So this will be shift from next value. This is 0, and again another toggling is happening here. So this will be 1, and this will be 1. Okay, so once this toggle is happened in your low to high pulse, we are actually I'll take this. So from this low to high pulse, here we are actually sampling the data. That means we are reading the data. Okay, so first value will be read, and that value will be 1. And then next the data will be toggled, and the next thing from low to high pulses, I'm just reading the data. Again, the next cycle, the data is toggled here. Again, here I'm just reading the data. So that is 1. Again, here it is toggled, and again here it is reading. So that is 1. So here, so this is how your data will be toggled, and the next cycle, the data will be read. Okay, is it clear how this data is toggled and how this data is reading? We already know in the synchronous communication.
What is the 2 lines indicate, sir?
These 2 lines indicates.
Serial clock have only indication, but most MOSI have 2 lines, right?
That is actually data. This is how we'll be denoting a data. So data will be always denoted in the square box like this.
Oh, okay.
Okay. Yes, is it clear how this data is toggling and how this data is reading? So we already know synchronous communication means your data transmission will be happen based on the clock pulse only. Okay, So this is how your clock pulse is actually changing the bits by bits, okay, as well as your data reading. Okay, so in our asynchronous communication, that is in UART, we'll be having a frame format. Okay, that start bit will be having one start bit from high to low. After that, you'll be having this data, whatever data you need to transfer, that data will be sent, and then there will be a low to high pulse for a start thing. Okay, so this width will actually defines your baud rate. Okay, that we already saw in the last class. Similarly, without this baud rate or kind of things, we'll be transferring the data based on these pulses. For each and every transition from low to high, your data will be toggled. Okay, and every transition from high to low in your pulse, your data will be reading. Okay, that is what happening over here. Okay, so this is for the type 1. Is it clear? I'll just explain the type 2 also so that you can able to compare what is happening with type 1 and type 2. So in type 2, that is your CPOL will be 0. Okay, and then C phase will be 1. Okay, so what is the C phase 1? C phase 1 means your low pulse will be the leading and high pulse will be trailing, right? Okay, so here what will happen? I'll just draw the same thing again. The serial clock, and this is your MOSI. So this is your serial clock, high to low pulse. This is your again high to low pulse, and this is again an high to low pulse, and this is again the high to low pulse. Okay. Now, since this phase here changes, that is this leading edge and trailing edges changes, what will happen? Your data toggling will occur from low to high. Okay, and your data sampling will occur in the high to low pulse. Okay, so the data tagging will be happen from low to high, right? So where it is low to high, this is my low to high pulse. Okay, again this is my low to high pulse. Again this is my low to high pulse. Okay, for each and every low to high pulses, my data will be toggled. So that's what will happen in the type 2. Okay, so that means here I'm just going to toggle the data from the low to high pulse, depends on this one. It is not reading. Oh, okay. Okay. So I'll draw this. Here my data is going to be toggled, correct? So here my data will be toggled. Okay, and similarly here my data will be toggled, and here the data will be toggled. And here again the data will be toggled in this low to high pulse. Okay. Similarly, every high to low pulse, I'm just going to read the data. This is my high to low pulse. Here I am going to read the data. Again, here I am going to read the data. Okay. So the same 1011, if I want to transfer, this will be my 1, this will be my 0, this will be my 1, and this will be my 1. Okay. So here the toggling is happening and I'm reading the data here. The toggling is happening again here. I'm reading the data. The toggling is happening. I'm reading the data. The toggling is happening and I will read the data. Okay. So for every toggling and reading, that will be happen in this low to high pulse to high to low pulse. Okay, so that is type number 2. Okay, so based on whether it is an trailing edge or a leading edge. Okay, so you can see every leading edge, your data is toggling. Okay, in every trailing edges, you are reading the data. Okay, so that will happen with the polarities. Okay, so type 3 and type 4 is the same thing. I'll just write it what it will happen. In type 3, the data toggling and data sampling will happen. Okay, so for every toggling will happen with the low to high pulse, and sampling will happen from high to low pulse. Okay, and in type 4, it is data toggle will be high to low, and data sample will happen from low to high. Okay, so why we need to define all these things is your clock or your data is completely depends on only the clock pulse in synchronous communication, correct? So in synchronous communication, how your data is going to be transferred, or when your data is going to be transferred, or what speed your data is going to be transferred, everything is depends on the clock pulse only. Okay, so when this data has to be toggled, and when I am going to read the data, okay, whenever it is toggling, I should not read the data, right? Because the value will be changed when before I reading it. Okay, so after reading from this toggle to this toggle, in this particular time, I can read it anywhere. Okay, so I need to define when this data has to be toggled from one bit to another bit. And during that gap, when I need to read this data, all these things will be defined based on only the clock pulse. We didn't have any other factors like a start bit or a stop bit or the baud rate or how many data bits, how many parity bits. All these things we will not consider here. Only this serial clock is what matters for toggling, collecting data. All these things will be done by only using this low pulse and high pulse of a serial clock. That is what called as in synchronous communication. Okay, clear?
Sir, type 3, type 2 looks same.
Yeah, type 3 and type 2 is same. Since the polarity changes, okay, this phase will be the leading and trailing will be the same, right?
Okay, okay.
So that
Yeah,
here
yeah.
this leading and trailing will be changed for the polarity. So here the polarity will
So
become 1, 1.
The one will be the toggling and one will be the for the reading.
Yes, yes.
Yes.
So this type 1 and type 4 is same, and type 2 and type 3 is same. Since the polarity is changing, the phase will be changing with the polarity. Okay, so this will be 0, 1 and 1, 0, and this 0, 0 and 1, 1 will be same. Okay, so that is what this SPI communication is. Okay, how this data will be transferred. Okay, now in STM, what we will do, we will just simply click a drop down box and select this clock polarity as a 0 and 1. It's a simple step. Okay, but for selecting that, why we need to select this clock polarity as a 0 and 1, we need to know all these things. Okay, so now we are going to open this STM UID. So we'll be configuring the pins, and we will. Oh, okay, so it's already opened. Okay, I already opened this. Okay, so I'm just going to configure this SPA. So I'll create a new. I'll just close all these projects. Just a minute. Okay. Okay, I'm going to create a new project. Here I'm going to select the board. For selecting the board, this one, I'm going to select this Nucleo F334. The same thing. And here I'm just going to give the project name as SPI underscore hardware. Okay. So now in this configuration pin, I need to configure the SPIs. Okay. So first in the system core clock, I'm just going to make this high speed as a bypass and low speed as a crystal ceramic. Okay, this is done. And in connectivity, here I'm going to use an SPI. Okay, so here I'm having only one SPI in my 334 board. So I'm just going to select the pin. And here the mode, okay, which mode I'm going to transfer the data. Okay, if I click this mode, here I will have a multiple options. Okay, whether I'm going to use it as a full duplex master or whether I'm going to use a full duplex slave or off duplex master or off duplex slave, or whether I'm going to only receive as a master or receive as a slave or transmit as a master or transmit as a slave. Okay, so if you want to use it for a particular mode, you can select it for that particular operation. Here I'm going to use it for the master mode for both transmission as well as a receiving. So I'm just going to use it as a full duplex master mode. Okay. So once I select it, here you can see the 3 pins are assigned. Okay. My clock, my MISO and MOSI. Okay. The slave select will not be assigned because slave select is nothing but it is an GPIO pin, right? So you can use any GPIO pin which is available for the slave select. Okay. That is our wish. It is not an system defined. Only this MISO, MOSI and clock will be defined for SPI. Okay, right. So now once this pin has been configured, we are just going for this frame format is same. Okay, here the data set, I'm going to make it as an 8-bit data. Okay, and here you can see the clock polarity and clock phase. Okay, for selecting whether it is a low or a high, okay, whether it has to be 2 edge or a 1 edge, for this configuration only, we have seen all these things. Okay, whether I'm going to make this clock polarity as a 0, 1, something like that, all these things for simply selecting one drop down box, we have just made all these things. Okay, but we need to know why this we are making it as a low or a high, right? For that only that theory part. Okay, so I'm just selecting the clock polarity as a low and clock phase I'm just going to select as a 1 edge. Okay, and everything else is same. So once you select all these parameters, the changes I made is only this as an 8-bit. That's it. Okay, everything else is same. Okay, so I'm just going to select this and Control S. I'm just generating the code for this SPA. Okay, so I'm just going to maximize this. Here you can see I'm having this handler for SPI1. Okay, and similarly, this SPA1 is configured over here as this master mode. Okay, it is in bidirectional 8-bit. I'm going to transfer, and my clock polarity is in low polarity, and all these things will be different. Okay, so now we are going to write the code in this while of one. Okay, so I'll just show you all 3 ways of transferring, receiving the data. Okay, before that, I need to declare some variables or some values So this is my private variable. Here I'm going to define uint 8 underscore t because I'm going to transfer an 8-bit of data. So I'm just defining uint 8 underscore t. This is tx underscore data. Okay, let's assume I'm going to transfer two datas. Okay, so one is it will be something like 0x AA. Okay, I'm just going to transfer 0x55, which is nothing but this is 1010. This is 0101. Okay, that two data I'm transferring. Okay, and I'm going to receive the same data in the RX data. Okay, so I'm just going to use an RX underscore data. I'm going to receive these two datas. Okay, again, this is something like a two data. So I'm going to transfer these two data and those two data will be received in this receiver. Okay, so that is what these two variables are for. Okay, now inside this while of one, for example, here in this IOC, if you just make it as only the full duplex transmit only master. Okay, if you made something like that, let's assume what you will do is here we have an API individually for transmission, individually for receiving, and for both transmission and receiver in a single AL API. Okay, so all these things we are going to see. First one is AL underscore SPI underscore transmit. Okay, so you can see we have a transmit, receive, and all these things we have. Okay, I'm going to transmit alone. Transmit, it is asking which handle I'm going to transfer. This one, which data I'm going to transfer. I'm going to transfer the TX data. Okay, and the size is nothing but it is a size of TX data. Okay, and the timeout, since it is using an polling method, I'm just giving 100 millisecond time delay for transferring the data. Okay, and if you want to receive the data, that is al underscore spi underscore receive. Okay, again the same thing, from which handle you are going to receive, where you are going to store the received data, that is my rx data, and what is the size of the data you are going to receive, that is nothing but the size of rx underscore data, and the timeout for each and every data received, again I'm just giving it as an 100. Okay, after that I will give al underscore delay. So every 1 second, you're going to transmit the data and you're going to receive the data. Okay. So this, I'm just going to build the code and check if there is any error. No error. Okay. So I'm going to debug it. I'll connect the board with the, okay, let's see if there is any field to female pin. Pin. Male pin. Okay. Let's just. So where my, okay, what I'm going to do is I'm just going to connect this meso to MOSI. Okay, that is my PS6 and PS7 has to be short. So I'll just go to this user manual, my PS6 and PS7, right? So I need to know where this PS6 and PS7 is. So this is my 334 board. Okay, PS6 and PS7, these two pins, correct? PS6 and PS, yeah, okay. So it is 13th and 15th pin. That is 1, 2, 3, 4, 5, 6, 7th pin and 8th pin I need to short. So left side 1, 2, 3, 4, 5, 6, 7th pin. And one more male to female. Okay. So I will check whether it is for this SPI, it is working for the single board. Okay. So I think I have built it. So I'll just click a debug. Okay. So yesterday, Yoraj, have you tried with that logic analyzer? Have you got an output for the UART?
No, sir. I tried, but it is not getting.
But you will get it. Okay, we will check it.
Let's will check it out.
You just need to configure over there. Okay. So first thing, I'm going to take this TX data. I'll paste it here. And similarly, this RX data, I'm going to paste it here. Okay. So the data which I am transferring here has to be received over here. Okay. That is what I'm planning. Okay. So if I resume and pass and get. Okay. The same board receiving and transmission is not happening for the communication protocol. Okay. So instead of having this separate transmission and receiver, you have a combined AP also. Okay. One is you'll be having al underscore SPI underscore transmit and receive. Okay, so there is one API which is called as a transmit receive API. That is which handle I need to use and what is the transmission data, that is TX data, what is the receive data, and what is the size of both this transmission data and receive data. Okay, so that we need to give. So you can either give it TX data or RX data because both are same. And what is the time? Okay. So instead of having two different APIs, you can actually able to give this in a single API also. That is possible. Okay. So run this and debug. Switch. Okay, I'm getting 255 to 55, but that is not the right value. Pin number is correct, right? 12 and 11.
So that slave select we need to do it. GPIO.
Since it is an same device, the slave select is not needed. Okay, if you are using multiple slaves or if you are using another device, then you need to select it as a slave. Okay, so here we are transferring the same board, right?
Yeah, I'm okay.
only this 255 is coming. Okay, I just try this one and check whether you are getting any answers. And Yuvraj, if you have this logic analyzer, you can check it with this. Okay, transfer the data and check whether you are receiving in the logic analyzer.
Okay.
Yeah.
Sir, SP. No.
Yeah, yeah, yeah.
Sir, இப்போ அதுக்கும் ground connect பண்ணுங்க sir.
இல்ல வேண்டாம். இன்னொரு டிவைஸ் நீங்க கனெக்ட் பண்றீங்கன்னா தான் அந்த டிவைஸ் நீங்க 0 பண்ணணும். இதே டிவைஸ் கூட தான் பண்ண போறோன்றதுனால அது பண்ண வேண்டாம்.
ஸோ டைரக்டா அப்படியே மோசி மிசோல கனெக்ட் பண்ணிடுவா.
ஆமாம், அப்படியே மோசி மீசோ மட்டும் ஷார்ட் பண்ணி விட்டுருங்க போதும்.
இல்ல அனலைசர்ல கேட்குறேன்.
அனலைசரில்
க்ரௌண்ட் கனெக்ட்
இதான்
பண்ணேன்.
உங்களோட மாஸ்டர் இல்லையா? ஸோ மோசி மட்டும் எடுத்துகிட்டு போயிட்டு ஒரு அனலைசரில் ஒரு பின்னில் கனெக்ட் பண்ணிங்க. மீசோ வேண்டாம். லாஜிக் அனலைசரோட ஒரு சேனல் எடுத்துகிட்டு போயிட்டு மோசியில் கனெக்ட் பண்ணிங்க. கிரவுண்டு கூட கனெக்ட் பண்ணிங்க. அவ்வளோதான். லாஜிக் அனலைசரில் கான்ஃபிகரேஷன் பண்ணுறீங்களா எஸ்பிஐக்கு?
ஜஸ்ட் ட்ரை பண்ணுறேன்.
சரி, ஓகே.
ஸ்க்ரீன் ஷேர் பண்ணுவா சார்.
ஓகே.
மோஸ்ட்லி வந்து சேனல் 0ல கனெக்ட் பண்ணிருக்கேன் சார்.
இல்லை, இது கேன்சல். க்ளோஸ் பண்ணுறோம். ஓகே. அந்த அசிங்க்ரனஸ் சீரியல் இருக்கு இல்லையா? இதில் நீங்கள் எஸ்பிஐ செலக்ட் பண்ணலாம். ஸோ மோஸ்ட்லி எந்த சேனலை செலக்ட் பண்ணியிருக்கீங்க? ஓகே.
0ல
மீசோ கிடையாது இல்லையா? சரி, விட்டுருங்க. கிளாக் கனெக்ட் பண்ணணும்.
கிளாக் வந்து
PA5 நினைக்கிறேன். PA5 கிளாக். புரிஞ்சுங்களா? அது 8 பிட்ஸ் தான். பொலாரிட்டி 0 தான் செட் பண்ணியிருக்கோம். ஃபேஸும் 0 தான் செட் பண்ணியிருக்கோம். ஓகே, சரி, சேவ். அவ்வளோதான். ஓகே.
இது delete பண்ணிடுறேன்.
அதை டெலிட் பண்ணிட்டு அது தேவையில்ல.
ட்ரிகர் ஏதாவது ஆன் பண்ணுமா சார்?
அது வேண்டாம். ஸ்டார்ட் கொடுங்க. அங்கே ப்ரோக்ராம் ரன் பண்ணிவிட்டு பில் பண்ணியாச்சா?
பில் பண்ணியாச்சு.
ஓகே.
ஒன் டைம் பில் பண்ணுவா.
ஒரு டைம் பில் பண்ணிட்டு ஓகே. சரி. வெயிட்டிங் ஃபார் டீபக்கர் கனெக்ஷன் டவுன்லோட். ஓகே. சரி, இப்போ போயிட்டு லாஜிக் அனலைசர் ரெக்கார்ட்.
டைரக்டா கொடுத்துருங்களா?
இல்லை கிளாக் பல்ஸ் உங்களுக்கு டிஃப்ரெண்ட்டாக வருது. அது கிளாக் பல்ஸ் இல்லை.
இல்லையா?
ஜூம் பண்ணுங்க. ஓகே.
0xAA and 0x55.
55. சரி, ஓகே. அந்த மவுஸ் மட்டும் அதுக்கு மேலே மூவ் பண்ணுங்களா? ரைட் கிளிக். ஆக்சுவலாக உங்களால் பார்க்க முடியும் என்ன டேட்டான்றது ஆஸ்கி வேல்யூவில்.
இதுல மாத்தலாம் சார். அந்த ஆப்ஷன் இருந்துச்சு இதுல பார்த்தேன்.
ஓகே.
இங்க இது அஸ்கில வச்சுட்டா சேஞ்ச் பண்ணலாம்.
ஓகே. ஆஸ்கியில் மாற்றிருங்க. ஜூம் இன். இன்னும் கொஞ்சம் ஜூம் பண்ணுங்க. இங்கே மேலேயே டேட்டா காட்டணும்.
இங்க காட்டும்.
ஆமாம். ஆக்சுவலாக எஸ்பிஐ பொறுத்த வரைக்கும் என்னென்னா, உங்களுக்கு கிளாக் பல்ஸ் ரெக்கார்ட் ஆகிடுச்சுன்னா மட்டும்தான் உங்களுக்கு டேட்டா ப்ராப்பராக டிஸ்பிளே ஆகும். கிளாக் பல்ஸ் வரலன்னா உங்களுக்கு டேட்டா வந்தாலுமே அது என்ன டேட்டான்றதை அனலைஸ் பண்ண முடியாது. பிரச்சனை இருக்கு. பட் டேட்டா வருதுல்ல. சேம் டேட்டா அகெயின் அண்ட் அகெயின் ரிப்பீட் ஆயிருக்கு. 1 செகண்ட் ஒரு தடவை வருதுன்னு நினைக்கிறேன். ஆமாம், 6 செகண்ட் ஒரு தடவை, 7 செகண்ட் 1 செகண்ட் ஒரு தடவை டிலே கொடுத்ததுனால வில் பி கெட்டிங் த சேம் 100.
பட் அது வேல்யூ
அந்த வேல்யூ மட்டும் நமக்கு ஆஸ்கி வேல்யூ டிஸ்பிளே ஆக மாட்டேது. ஏன்னா கிளாக் பல்ஸ் உங்களுக்கு ரெக்கார்ட் ஆகலை. கிளாக் பல்ஸ் பிஎஃப்ஐ கரெக்டாக கொடுத்துருக்கீங்களா செக் பண்ணுங்க. லாஜிக் அனலைசர் சேனல் கரெக்டாக செலக்ட் ஆயிருக்கா? இங்கே இல்லை, அந்த பின் கரெக்டாக செலக்ட் பண்ணிருக்கீங்களா செக் பண்ணி பாருங்க. ம்
ஒன் செகண்ட் செக் பண்ணலாமா சார்? பின் சேஞ்ச் பண்ணிருக்கேன்.
ஓகே.
டேரக்டா ரன் பண்ணலாமா?
அப்படியே டேரெக்டாக ரன் பண்ணுங்க. அங்கே ரன் பண்ணிவிட்டு கோட் ரன் பண்ணிட்டீங்களா?
கோட் ரன் பண்ணல. ஒன் செகண்ட் ரன் பண்ணலாம்.
கோட் ரன் பண்ணணும். திருப்பி பில் பண்ணிட்டு ரன் பண்ணணும். பில் பண்ணியாச்சா? சேஞ்ச் பண்ணதுக்கப்புறம் ஓகே.
பண்றோம்.
ஓகே. இங்க கீழ கிளாக் பல்ஸ் கொஞ்சம் ஜூம் அவுட் பண்ணுங்க. ஓகே. இட் இஸ் 1010 சாரி 010101 இங்க 101010 இருக்கா? ஓகே. டேட்டா கரெக்ட் தான். பட் இட்ஸ் நாட்
இதுல
ஷோயிங்
talk
எனி
பண்றேன்.
வேல்யூடா. ஓகே, வேல்யூ ஷோ ஆகுது. கோ டு பைனரி.
எதுவுமே கண்ட்ரோல்
இல்ல. Okay. So others, this is how you will be visualizing the data in the data analyzer. Okay, or logic analyzer. So the data which you are transferring from the MOSI is recorded in the channel number 0, and channel number 2, that is D2, is having the clock pulse. Okay. So whenever we are having this clock pulse, the data will be transferred. Okay, so that is what this logic analyzer is recorded. Okay, on the same board communication is not happening. We still need to check that one. I have shorted this MOSI with MISO, but the data is not recorded here. We need to check it. Okay, but this is how we'll be transferring the data as well as receiving the data. Okay, if you have another board, you can connect this MOSI to MISO of that board and MISO to MOSI of this board. And apart from this, you just need to make one digital pin as a logical 0 for the slave select. Okay, so make that as a slave select, and then you can able to communicate with the multiple devices. Yes, so that is possible. Yeah. Now that is for measuring the width.
பட் ஆனா லாஸ்ட் டைம் வந்தது சார்.
லாஸ்ட் டைம் அந்த இதுக்கு
டைமர் பண்ணும்போது
சிங்க்ரனஸ் கம்யூனிகேஷனுக்கும் வரும். நீங்க இப்போ ஹெலோன்னு அனுப்பிச்சிங்கன்னா ஹலோ வில் பி டிஸ்பிளேட் ஹியர்.
டேட்டா மாத்தி பார்க்கலாமா?
டேட்டா மாற்றி அதை செக் பண்ணி பாருங்க. பட் வாட் யூ ஆர் கெட்டிங் இஸ் கரெக்ட். ஓகே.
கேரக்டர் ஏதாவது கொடுத்து பார்க்கலாம் சார்.
கேரக்டராக கொடுக்குறீங்களா? சரி, ஓகே. ஆனால் 8 பிட் தான் அனுப்ப முடியும்.
ஒரே ஒரு கேரக்டர் மட்டும் அனுப்பி பார்க்கலாமா?
equal to A. ஓகே.
இது ஒன் பட்டன்.
அது வேணாம், நம்ம RX இங்கே யூஸ் பண்ணல. இட் கேன் பி 2. பட் டேட்டா ட்ரான்ஸ்ஃபர் அண்ட் ரிசீவ்ல
இதுவும் கேரா இருக்கணுங்களா?
சரி, ஓகே, ஒன்றும் பிரச்சனை இல்லை. பில் பண்ணி பாருங்க. We will check it. Okay. That is we are passing the two arguments of different sizes. That is the issue. பரவாயில்ல, நம்ம அங்க TX டேட்டா மட்டும் தானே ரெக்கார்ட் பண்றோம். ஓகே, ரன். Okay, record.
Oh my God.
ரன் ஆயிடுச்சா?
நல்லா இதை ஸ்டாப் பண்ணேன். ரொம்ப ஸ்பீடாக போயிடுச்சு.
ஓகே,
அங்க மாத்திடலாங்களா? இதை மாத்திடலாமா?
சரி, ஓகே. ஒன்
கேராவே போட்டிருக்கேன்.
ம் ஓகே. கீழே 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 ரன் பண்ண வேண்டாம், ரன் பண்ண வேண்டாம். இந்த தான் சைஸ் ஆஃப் இருக்கு இல்லையா, மேக் இட் as 1. இது ஃபுல்லாகவே ரிமூவ் பண்ணிவிட்டு மேக் இட் as 1. ம்
No, it is too warnings.
ஓகே. think we can't able to transfer. Okay, no issues. Run.
இதை வந்துச்சா?
இல்லை, பிளாக் ப்ளஸ் வேறு ரெக்கார்ட் ஆகல. ஓகே, do one thing. Unsigned integer ஆகவே கொடுத்துங்க instead of character. Change it to unsigned integer. ASCII வேல்யூவை கொடுத்துக்கலாம். ஓகே, சரி. இங்கே வந்து 0x கேபிட்டல் ஏக்கு என்ன 65, 0x 65 ப்ராக்கெட் வேண்டாம், நார்மலாகவே 0x 65 ஒரு வேல்யூ தானே. ஓகே, பில்
சேம் லைக் கீழே சேஞ்ச் பண்ண சைஸ்.
ஒரு பைட்டு தான் அது.
சேம் அப்டேட் பண்ணுமா?
பேர் டர்ன் பிரச்சனை இல்லை, ஒரு வேல்யூ தானே.
சைஸ் ஆஃப் கொடுத்து பார்க்கட்டுங்களா?
சரி, ஓகே. give size of same 8 bit 1 byte. Okay, same thing. Okay. டேட்டா இது மாதிரி ரெக்கார்ட் ஆகவே இல்லையே.
இது மிஸ் கான்டாக்ட் ஆயிடுச்சா?
கோட் போங்க.
ஆமா.
ஐ மீன் STM ரன்ல தானே இருக்கு. ஓகே, ஒரு தடவை டீபக் மோட் போங்க. ரைட் கிளிக் SPI ப்ரோக்ராம் டீபக் மோட். switch. Resume. Left side now. Resume. Okay, இப்போ ரன் பண்ணுங்க.
Data line. எஸ்பிஐ கிளாக்கே வரல, டேட்டா வரலன்னா கூட. Contact right up. ஆனால் டைட்டாக தான் இருக்கு. நேற்று டைமராக இப்படிதான். டைமர் யூஆர்டா இதே மாதிரி தான் இருந்துச்சு. ஒரு வாட்டி வர மாதிரி இருந்துச்சு, நெக்ஸ்ட் டைம் அப்புறம் வரல.
வரவே இல்லையா?
நேற்று நைட்ல உட்காந்துருந்தேன், 10 மணி வரைக்கும் உட்காந்துருந்தேன், ஆனாலும் ஒர்க் ஆகல.
இது நான் என்னன்னு பார்த்துட்டு சொல்றேன். லைக் சேம் டிவைஸ் ஹவு டு ட்ரான்ஸ்ஃபர் த டேட்டா அப்படின்றது. ஓகே, வில் see this.
செக் இந்த பழைய டேட்டா போட்டு பார்க்கலாம்.
சரி, ஓகே. இங்க 2 RX டேட்டா.
மவுஸ் கொஞ்சம் ப்ராப்ளம்.
ஓகே, இது டெர்மினேட் பண்ணிட்டு ஒரு தடவை பில் பண்ணி பாரு. அது கரெக்டாக தான் இருக்கு. இப்போ வருது. மேலேயே தெரியுது.
கேம் வந்துச்சு சார்.
ஓகே,
ஆனா ஏஐ மட்டும் தான் வந்திருக்கு.
ஜூம் பண்ணி பாருங்க.
ரெண்டு கிளாக் வந்திருக்கு சார். ஃபர்ஸ்ட் டைம்
ஆமா.
ஒன்று தான் வந்திருந்தது.
So this is for 10. Sorry, this is for AA. AA is 10 and this is for 55. ஓகே சார், இப்போ இதுலயே இந்த இதுலயே வேற ஏதாச்சும் வேல்யூ, இந்த அரேலயே வேற ஏதாச்சும் வேல்யூ இருந்தா கொடுத்து செக் பண்ணி பாருங்க, அதே வேல்யூ வருதான்ட்டு. ஓகேவா? This is for SPI.
வேற 0011 போடலாம் சார்.
எது வேணா கொடுங்க, கொடுத்து செக் பண்ணி பாருங்க. ஓகே, ஜீரோ ஜீரோனா பல்ஸ் எதுவுமே தெரியாதுல்ல. மேக் இட் 0101. ஓகே,
001. பட் இது சிங்கிள் டேட்டா பண்ணலாம்.
ஆக்சுவலி சிங்கிள் டேட்டா அனுப்ப முடியும்.
ஒரு வாட்டி ட்ரை பண்ணியிருக்கேன். அது வந்து அந்த நம்பரை தவிர வேற எது போட்டாலும் வராது.
1000 தவிர வருதுன்னு வரலையா?
இருக்கு சார்.
இருக்கு.
வந்துருக்கு.
It is 1001. So it is actually 0001. இது வந்து 00000001. கரெக்டா? So 10 னா it is 0001 0000. அதான் 10. கரெக்டா? 01 னா you will be having 7 zeros, last 1 வரும். ஓகேவா?
ஓகே.
So this is how we'll be transferring the data from SPI to another device. Okay, if you have a receiver device, you can transfer this sending data to the receiver device. And in IOC, you can just configure it as a sender only, receiver only, or it can be transferred, configured as both sender, receiver, master, and slave. Okay, so that you can able to configure. And so this is for master slave device. Okay. Okay, I'll just share the screen. Just a minute. Stop share. Okay. So if you want to make it as the slave select pin, okay. So here you have only these 3 pins, right? Okay. Let's assume you are going to use a slave mode, and for that slave mode, you required an slave select pin, right? Okay. So for that, what you need to do is just select this full duplex slave mode. Okay. And then select this hardware NSS input signal. Okay. This hardware NSS is nothing but it is an slave select. Okay. Click this and you'll get this slave select pin. Okay, so from master, you just need to make this PA4 as 0. That's it. So if you select this PA4 as 0, that means this slave device will be activated. Okay, so that is what the slave select pin is for, this NSS pin. Okay, so if you have multiple devices, you can make one as a master, one as a slave, and make this pin as a slave select pin, and you can just make this 0, and you can able to transfer the data, and you can able to receive the data from this particular slave. So that is possible with this. Okay. So this is what an SPI communication is. So we know what is SPI communication, how to transfer a data, how to receive a data, and what this clock polarity, clock phase, and all these things. So that is what for this today's session. Okay. So today is Wednesday, right? And we'll be having our next class on Monday. So as I already said, I'm going for this Coimbatore workshop. Okay, so I'll be traveling from tomorrow. So I couldn't able to take the class on tomorrow and day after tomorrow since the event is happening. We will have the next class on Monday. Okay, so still we will have I2C, and I will take CAN protocol. Then we will see the startup code, that is bootloader, that we will see on Wednesday. So most probably next Wednesday or Thursday we will finish this device driver. Okay, so after that we will start our bare metal, RTOS program, RTOS module. Right, so mostly by next week we will finish our device driver module.
Sir,
So,
I have another Arduino board, so I can connect this with that, right? I mean, this
Mm,
STM32 with
Arduino. But you need to
master
make
and slave. Act as
but you need to make that Arduino as a slave.
okay. I'll do research on that. Okay, sir.
Okay. Yeah.
Sir,
Yes.
I'm not able to generate the code.
You need to log in to the STM account, Mohammed. Then only
Okay.
you can able to log in. I mean, you can able to generate the code.
Okay, and one more thing, I have same board what you have, but for
Mhm.
that SPI one is not available. No, it's
334.
yes.
Mm, okay. Can you share the screen?
Yes, sir.
Has to be there.
The screen is visible, sir.
It's actually black. Now it is visible. This is not the board which I am having. It has multiple I2Cs, multiple SPI. Who can? Okay, can I just zoom into that? Okay, click that particular board. I mean, click it anywhere. Okay, press Ctrl M. Control, yeah, okay. Oh no, this is 446.
Okay.
I'm using STM32F 334.
Okay, okay.
Yeah,
This
this
is
is
what
334.
they have mentioned. Vijay mentioned.
Yeah.
Okay.
Currently having this in my home. Okay, this 446 is available in the office. So since
Okay.
I'm taking class from home, I'm using this 334, which is my personal board that I'm
Okay,
using.
sir.
You can select SPA2 also, no issues.
Okay. So, where to log in, sir?
Go to this window. Sorry, help. Help. Yeah. Okay. Go to this configuration tool. Manage embedded software packages. Okay, so you're using F4, right? Okay, just scroll down. You will find STM32 F4. Others you can leave. Okay, I'll just see them. Others you can leave. We'll see on Monday. Okay, bye.
Thank you, sir.
Yeah, thank you. Bye.
Thank you, sir.
Yeah, thank you. Bye. Yes, Mohammed. Click that first one. The checkbox on the left side. Click the checkbox. On the bottom, there is an install, right? Click that install. So this is the package for the particular board which you are using. Okay. Now click enter ST account. There you can able to log in. So once you logged in, this package will be downloaded and it will install. After that, you can able to generate the code.
Okay, sir.
Okay. Yeah.
Okay. And sir, recordings will be available, no, for today's till
Yes.
today's class.
Only yesterday's recording I didn't put in the
Okay.
drive. I will put it now.
Can you share that drive link, sir?
Link. The link is already available in the group, right?
Actually, I lost the WhatsApp content.
Okay.
Everything.
I'll just pin it on the top.
Okay, sir. Thanks.
Yes. Okay.
Okay, thank you, sir.
Sir, one
Okay.
doubt. I just want.
Yes.
Share this. If we're okay. Yeah.
Okay.
Sir, so what is this USB OTG, sir?
USB, what is it? Okay, can I just click this?
Yes, sir. It just came here. It was the host only. It clicked automatically. I mean, that's what I'm asking.
Okay. So you're using that development board, right?
Yes, sir. development.
Actually, with this, you can be able to, transfer the data or receive the data through this USB.
So for that, I need to dual role or
Yeah. For example, if you're going to transfer the data or if you're going to receive the data, then you can able to use it as a host only or device only, something like that, or dual role, both this host and device.
and if I click SPA1, if I select this, it's showing something like numbers and also that's what I don't understand this.
That is fine. That serial number is fine, but the name is serial clock, serial MISO, and serial SPI MOSI, right? So that is okay.
Okay.
Yeah.
Okay.
You can actually able to change that name also if you want. Like,
okay.
can you just go to this GPIO? Not here. On the left side, there is a GPIO, right? This connectivity.
Left side. Yes.
On top. Go to this GPIO. System core, GPIO. This is PA5, PA6, right? Okay. Have we clicked it? Okay, just open this configuration. Click this SPA.
Yes.
Okay, you can click that any particular pin and you can able to change the name also. On the bottom, if you just scroll down, you can able to change the user label.
Okay. Okay.
Yeah.
Okay.
Okay.
Thank you.
Yes.
Thank you.
Okay, thank you. Bye. Okay, guys. Thank you. Bye. We'll see you on Monday.
Thank you, sir. Bye.
Thank you. Bye.
Sir, recordings are available for download. Sometimes I have a power outage. That's why I'm asking.
It's only viewable option. We won't actually provide it for the downloadable.
Okay.
Yeah.
Okay, sir. No problem.
Yes. Okay.
Okay, sir. Thank you.
Okay, thank you. சொல்லுங்க சரியா?
ஹலோ சார், கேக்குதா சார்?
கேக்குது சரியா, சொல்லுங்க.
சார் என்ன பிளேஸ்மெண்ட் பத்தி எதனா விஷயம் தெரிஞ்சதா சார்? எதுவும்
பிளேஸ்மெண்ட் ஆக்சுவலா விஜய் தான் பார்த்துட்டு இருக்காரு.